Hey guys, so we're gonna go over the AVL tree. So I'm assuming that you guys already know binary search trees. So just moving on from that, going on to the AVL tree. So AVL stands for the three inventors. Do not remember off the top of my head, but they created a tree that basically balances itself. So with a binary search tree, if you were to insert these numbers in order, the tree could be really funky looking and not balanced. Let's say if you had, I don't have them written here, but if you were to have 1, 2, 3, 4, 5, 6. So let's just kind of go with this example, and let's just say we went in order from the left to the right, inserting these nodes into the tree. So we'd start with 1. Okay, that would be the root, and then we're going to go to 2. So 2 is larger than 1, so it's going to go to the right. Okay, let's go to 3. 3, larger than 1, larger than 2, it's going to go to the right. 4, larger than 1, larger than 2, larger than 3, going to go to the right. Now you can see this tree is not balanced out. It just keeps getting longer, and it's basically how many, let's see, we have a total of 6. We're going to have a total of 6 nodes when we get to this guy and put it in the tree. And the height of this tree is going to be n. It's going to be 6 because it just keeps going out to the right. And when you build that tree, as far as searching through that tree, it's going to take you a long time. You're going to have to go through every single node to find 6. So that's not what we want. So that's where we have the AVL tree. So it's a tree that when you insert it, it's going to check to see if it's balanced. Okay? So let me talk about a balanced tree just in case you guys don't know. So let's say, let me build a tree here real quick. And let's do this guy. Okay, so however you tell if a tree is balanced is you're going to take basically the root node or every node, and you're going to check to the right and to the left, the height. So how we do that is let's check the balance of this top root node here. So we have one node here. Now it's the furthest pass. So basically a lot of people say count the edges, 1, 2, 3, or you can just count the nodes and the longest path. So 1 node, 2 node, 3 node. So the height on the right side of this node is going to be 3. And then if we look to the left of the node, we see that it only has 1. So the height is 1. Okay. Now why did I do 3 minus 1? Because to check the balance of a tree, so balance is the height of the right minus the left, the height of the left. So balance of a particular node is going to be the right height, which in this case is 3, and then the left height, which is 1. Okay, so we know how to check the balance, find the balance. So it's going to be 3 minus 1 equals 2. So the balance of this node is 2. Now that is not good. Now obviously we can look at this and say, hey, it's obviously unbalanced, but that is the way to check, basically mathematically. Now what we're looking for a balanced tree is we're either looking for a -1, a 0, or a 1. So basically what we would do is we'd check every node and see what the balance is. We would check the right of this node and check the left, and then subtract the right from the left to get the balance. And we do that for every node. And if the tree is balanced, or if the node is balanced, it is going to be -1, 0, or 1. So in this case, we have 2. So obviously we can look at this and know that it's unbalanced, but now that we actually did the calculations, we know that it's off by 1, because it's not a -1, it's not a 0, and it's a 1. So how do we fix that? So that's what the AVL tree is going to do. Okay. So actually, let me show you before we actually insert numbers into the tree. Let's do that example that I just had up there. So this guy. So this tree is unbalanced. This is unbalanced, but basically the tree is always going to be balanced when you have an AVL tree. It's always going to be balanced when you insert, and then when you insert this node, this is when it gets unbalanced. So basically, the balance of this node is 1 on the right and 0 on the left. So we know it's 1 because the right minus the left, this is just null. Let's just not have that there for now. And if we check this tree, the height is 1, 2 on the right side, and the height is 1 on the left. So 2 minus 1, 1. Now, this guy, we check the balance. 1, 2, 3 on the right, 1 on the left. That's 2. So we know this tree is unbalanced, kind of like I said in the previous. But how are we going to fix that? So we inserted that node, and basically the process is going to be, so let's say this is 2, this is 1, this is 5, this is 4, 6, and 7. Okay, so what's the process of doing this? So in our case, we are going to do what's called a right-left rotation. So basically, what we're going to do here is we're going to, and I'm going to try to show you the best way to look at this. So basically what we do in this situation is we're going to take this node right here, and a lot of times you're kind of always going to picture this. This is how it worked for me. You're going to picture these two almost arms trying to pull itself up. So that 4 is going to try to sneak up here and become the root. Now, right left, why is it called right left? The best way I like to remember this is because this is the node we're looking at that's unbalanced. To get to that first node that we want to move to the root, we have to go to its right node, and then from the right, we need to go to the left. So right, left. That's how we get to the node that we need to move from the unbalanced node. So we're going to take that node, and it's going to become the root. So once we do that, let's see here. That's going to become 4. This is going to become 2. And 2 becomes 1. So, because we pulled him up and he came here, and then the 2 came there. That was on the left. The 5 still stays there. Okay. Now, let's see what we have. So, let's see what the balance is. So, what we're going to have here is 2 nodes on the left and 3 on the right. So 3 minus 2 is 1. Okay. And then this node, it has 1 on the left and 1 on the right. the difference between the two is 1. That's okay. This node, it doesn't have any children, so the balance is 0. So this node, or here, let's check this guy. This one has 2, and then on the left it has 0. So right now, 2 minus 0 is 2, so that's the balance, and that's not equal to negative 1, 0, or 1. So what we're going to do here is what's called now this is an easy one, a right-right rotation. And I like to think of it as this is the node. That we're working with. And we're going to go to the right and then to the right again to get to this guy, and then we're going to push it up. Now, a good way to, usually the LL and RR, the way I like to see it is pretend that, this is a good analogy that I've learned, is to pretend that's a nail, and this is basically a string of something, and you're going to pull it over the nail. So you're going to go that way. Well, I should write the arrow the other way. You're going to go around and over the nail. Okay? So this is the node that is unbalanced, and we, you know, it's not a left RL or a LR because it's kind of like in a straight line, and you could tell it's kind of an easy one. So what we're going to do is just pretend that nail's here, and we're going to pull this over the nail. So when we pull it, this is going to become 5, this is going to become 6, and this is going to become 7. And this guy is obviously gone because that was 7. Okay, so that kind of shows you, you know, the different rotations, because there's going to be RL, LR, and then left, and RR. So there's going to be 4 different ones, 4 different rotations that you're going to use. But anyways, let's get to the AVL tree. So the AVL tree is basically using this concept that we just talked about. It's keeping that tree balanced. So let's actually dive in. So let's start with 15. Insert 15 into the tree. It's going to be the root node. Let's check its balance every time we insert a node. So right now, the balance, this is null. This is null. That's basically 0 and 0. The balance is 0. Now I'm going to get rid of these nulls. I just want to explain to you guys, especially when you actually start coding, that those are nulls. The children, the right and the left child are nulls. So the balance is 0. Let's insert the 5. The 5 is less than 15, so it's going to go to the left. Oh, and let's check the balance. So the balance of this guy is going to be 0 on the right and 1 on the left. So it's -1 for the balance, which is okay. That's a balanced tree. And then obviously these two guys are 0, so the balance of this is 0. So we're fine. Okay, and then now let's insert 35. So 35 is greater than 15, so it's going to go over here. Now the balance of this is 1 on the right, and so there's 1 node on the right of this node, and then 1 on the left. So 1 minus 1 is 0. And obviously these two guys are going to be 0 because they don't even have any children. Okay. Let's take 3. Let's insert 3. 3 is less than 15. 3 is less than 5. Okay. What's the balance here? Let's check the balance. So we have 1 on the right and then 2 on the left. So that is -1 for the balance. The balance of this guy has 1 on the left, or 0 on the right and then 1 on the left. So it is -1. And then this is still 0 because he doesn't have any children. Let's take 6. So enter 6 into the root node. 6 is less than 15. 6 is greater than 5. 6 goes here. Hey, the balance changes because there's one on the right and one on the left. You subtract the right from the left, and that equals 0. I'm just trying to be repetitive to really drill this into your mind or in your head. Okay. So the balance, the longest node on, or the longest path on the right is 1 node. The longest path on the left is 2 nodes still. So you're still at -1. 57. Let's insert 57. So easy one. 15. It's greater than 35. 57. Okay. What's the balance? 2 nodes to the right. The longest path. 2 nodes to the left. Longest path. The path is 0, or the balance is 0. 1 node to the right, 0 to the left. 1 is the balance. And then obviously 0 for this guy. Now I ran out of numbers, but let's just add some in to get, because obviously this is an AVL tree and we haven't really experienced what happens when you insert a node and it gets unbalanced. So let's see what we want to add here. Let's add a 56. Oops. Let's add a 56 to the tree. So 56 is going to come down here. Greater than 35, less than 57. 56 is here. Okay. So let's check the balance. So 1, 2, 3 on the right, longest path. 1, 2 on the left. So it's got a balance of 1, and then this is going to be 2, right? So if you look at this node here, to the right, it has a path of 2. To the left, it has 0. So it's an unbalanced tree right now. So this is where AVL comes in handy, because you do not want to create an unbalanced tree. It's going to fix it right away. As soon as you insert the node and it finds out that it's unbalanced, it's going to fix itself with the algorithm. Okay. So what we're going to do here is, so what happened was, it was a right, we inserted to the right and then to the left, but this one is actually going to be an easy fix, okay? So what we're going to do here is, you can almost, a lot of times you can spot it out. So this is the guy that's unbalanced right here, the 35. He doesn't have any left children, okay? So this is going to be an RR rotation. Now, there's different ways to think of it. I like to think as this node's right child and then right child again. When you're programming, you'll see kind of why it's called it, because you have to take the right of the right to get that guy moving. Okay, so basically we're going to use whenever it's RR or LL, well, remember, we're going to use the nail. We're going to use the nail to pull this over. We're going to pull that over the nail, over here. So it's going to rotate this way. Okay. So let's do that. Let's do that right now. So when we pull it, 35 is going to go here. 57 is going to go up here. I'm sorry, let me clean this up. I need an eraser. So 57, and then 56, because we're pulling everything up over the nail. We'll just keep that nail there. 56. Okay, so and you can double check by looking at the tree, and I goofed something up here, guys. Sorry. Hold on. I had 57 and 56. Okay, so it's 35, 56, 57, right? So I might have did the wrong rotation, which is okay because you guys are, you know, we all make mistakes. We'll run into this stuff that we have to fix. 57 and then 56. So that's nice because we can always check. So sorry guys, we did the wrong rotation, which is okay. I mean, you guys can understand this with me. That's the good thing, you can always check yourself. So if we pulled it over the nail, we would have had 57 up here and then 56 to the right, which would have been wrong because 56 is not greater than 57. So this is where we're going to do the right-left rotation. And you can also think of it as we inserted to the right of this node and to the left of this node, and that's what caused the unbalance. Is from the node that's unbalanced, we went to the right and then to the left, and it caused an unbalance. So we're going to use the right-left. So sorry guys, we'll fix this though. We'll still learn. So right-left rotation. So remember this guy here? So it's kind of like he's going to push himself up into the root spot. That's how I like to view it. So when he pulls himself up into the root spot, what is it going to look like? So 57 is actually going to stay the same. And then 56 is going to go here. And then its pointer, he's just going to push him down there. That's where 35 is going to come into play. So hopefully I didn't confuse you guys too much with that little mistake there and I did the wrong rotation, but you'll get the hang of it with a little bit of practice. But I'm still showing you how the AVL tree is going to work. So let's get rid of this and let's check the balance of our tree. So this is a little longer than the other one, but that's okay. Let's bring this down so it actually looks balanced. 57. So we know 57 is greater than 56 and 35 is less. That's right. We did an RL rotation because we inserted to the right and to the left, and that caused the unbalance. So now we can see that the balance of this node here to the right and to the left is 1. 1 minus 1 is 0. The longest path to the right of the root node is 1, 2, or you can go either way, 1, 2. So 2, and then the longest path to the left is 1, 2, so the balance is 0. All right, guys, so I'll probably do another video on the AVL tree to do some different rotation or some more rotations, especially since I goofed up on that one, but we fixed it. But I'll probably do the left-right rotation and maybe a left-left rotation. But hopefully that helps and you guys got the hang of it. If you guys do have any questions, drop them in the comments. Thanks.